The idea for today is to basically go through a couple of slides here, discussing chapter 3, okay? And just give you an idea on what linear neural networks are, some of the most important components and support. And oh wow, so loud outside. Just give me a second, folks. Let me just try to see what's going on. Oh wow, sorry about that. Kind of like a little accident outside, but I think everything's okay. All right, so let's continue. This is where we are. We are in chapter 3, right? Linear neural networks. We're going to start to talk about some basic components, and then eventually move on to. Let me just make a full presentation. And then later on, we're going to move into multi-layer perceptions, where it starts to get really interesting, and you start to see things that are more common these days in deep learning. And so you'll start to see some more interesting things. So the agenda for today, I'm going to do a brief summary of the chapter 3, discusses linear regression and softmax regression, right? These are the main two methods for basically implementing very basic neural networks, linear neural networks in particular. And I also have a code session. Most of it is going to be about code, and try to explain to you, for those of you, that are starting with PyTorch, give you an idea on how PyTorch works and how to actually build a model. Of course, everything is adopted from the book, but I'm going to explain to you how that code works and so forth. So I'm going to talk about the implementation from scratch, which is great because this is how you actually start to begin to understand how to actually build models and neural networks. And you'll start to understand this idea of the computation graph and how it makes sense when you're training things. And then the concise implementation is obviously what you see today when you see an implementation. For instance, say a paper implementation, you see concise implementations, which is leveraging those high-level functionalities of these different toolkits like PyTorch or TensorFlow or MXNet, right? So you don't actually see what's going on, all the details, but you only see the high-level use, say, of linear layers and nonlinear transformations and these sort of things. And softmax regression, of course, more for classification problems, right? We're going to talk about softmax a little bit, what it is and what it achieves. And I'll actually talk about, in the coding session, the introduce the image classification data set. This is where we usually start. I actually wanted to do a different thing, wanted to do more like an NLP use case, but didn't get enough time to actually do that. But I think the image classification data set is quite good. It's using the fashion MNIST, which is the fashion data set, which is really great to actually start with. I think I started to understand some of the functionalities in PyTorch and how to build models. And then implementation from scratch as well. And then there's a concise implementation. I'm not sure if there's actually a concise implementation but I think there is an implementation from scratch. So I don't remember quite well if I actually put in that code there. But I think it'll be enough for today. So linear regression, right? Regression is what's used for modeling relationship between one that should be a one more independent variables and a dependent variable, right? What does that mean? As an example, imagine there's like housing prices which you want to predict. So what would you use as your the independent variables, right? You would use like size, say, of a property or something like that. The location could also be important for predicting those prices, and there are a lot of things like how many rooms and so forth. So those are independent variables. Dependent variable is the pricing itself. And you can see some examples here, right? But the idea of this linear regression is to train a model is able to predict that numerical value. This is a continuous value, of course, right? And then there's no limit to what this value can be here, and depending on the use case, of course. And you have many examples here: predicting prices, predicting length of stay, say in a hospital, and demand forecasting. These are the examples explained in the book directly. So that's the ones I use here. But there's so many other examples of linear regression. And linear regression, one common confusion is that, of course, people confuse it sometimes with classification. People that are getting started with machine learning in general, these are two different things. Classification, with linear regression, we're interested in that numerical value, predicting that numerical value. The classification is we want to make like a hard assignment, for instance. Sometimes there's cases of soft assignment as well, but hard assignment means maybe you want to label a picture as cat or a dog, or you want to identify it as a positive or negative tweet or something like that, right? That's what we refer to as the hard assignment. But later I'm going to discuss what the idea of classification is. We're going to get started with linear regression as a beginning, right? So aiming to predict, classification aims to predict the set of categories. Okay, so very rough notes I put together here. I think I just wanted to highlight some of the most important points in the chapter. There's a lot of content there. I mean, it's very, I think, in my opinion, it's very beginner friendly. There's a lot of details, unnecessary details in some sense. But I think it's great because if you really want to dive deeper, it gives you some ideas on where to actually search, right? So this idea of the, for instance, the maximum likelihood estimate, what is this about? How do we actually use those principles when we are designing neural networks? How do they actually, what's the role of this and this principle? So there's some guidance there. There's even some links where you can actually go and read and try to understand where this concept comes from. And if you actually go into books, there's like all types of derivations, all types of equations that are actually adopted in machine learning. And this idea of the probabilities and why that makes sense when you're training neural networks, all of that stuff, I think the book does a really, really wonderful job there. And I think the purpose was to give an idea on where to go look for more content and get an idea of what's going on. But yeah, they try to keep it very minimal in that sense, but they give you still that little hint where to go look for things. So what's the idea of linear regression and the basic elements, right? The assumption, of course, there's always an assumption when you're working in the context of machine learning, right? You always have this kind of assumption, right? You're building this model, you want to establish some linear relationship between the independent variables, I give you the example, and the dependent variable y. And you start to introduce some notations, but in the next slide, we'll show you a bit of the notations that's used in the book. And I like it, that's very consistent. And typically, this is the notation that you would see in papers and so forth. And why it can be expressed as a weighted sum of the elements. Remember the weighted sum, we spoke a little bit about, I don't know if you got a chance to look at it more, but we discussed this operation when we discussed preliminaries. We discussed the operations, the dot, right? The dot product, right? That's the weighted sum. That's how you would get the weighted sum of the elements. And that's how this y would be expressed. Given some noise on the observation, what is this noise about? Of course, that's the assumption we're making, that it follows some Gaussian distribution. That's the idea. Of course, the observed data, and that's something that we use and we leverage, right? Based on this assumption, we can come up with all our equations that we're going to use to say, come up with our last function. How do we actually output probabilities and all these different things? So we always start with this fundamental thing, this assumption. And you can read more on the chapter more about the Gaussian distribution and how well it plays. And I like that there are some equations that are given, but I think you still can go, you can go further trying to understand it. And I think the book doesn't really provide you a link to that, but maybe I'll try to come up with some links to give an idea on what actually from this idea do we actually use in machine learning and deep learning specifically. And I'm going to try to work on that because I think it's really important if you want to gain more intuition. But if you just want to apply it, I think up to this point, you don't really need to go further. All right, so the example here is we would like to estimate the price. Oh, sorry. I'm just checking here that everything is still working. I'm afraid that my computer is just giving a lot of trouble these days, but yeah, everything's okay. So the example is we like to estimate price of houses based on area and age. You can see the table there, right? You can see that we have area and age. We sometimes refer them as features, the same thing as independent variables. And then your dependent variable is a price. That's a typical linear regression problem. Actually, very classical example here with the area, age, and the price, and so forth. But these examples that I provide here is just to give an idea of how this data would look. But These are actual real examples. And we want to develop a predictive model for predicting those house prices. So what we're interested in is actually developing these predictive models. And what concepts do we actually need? What are the components and the pieces that we actually need to develop this predictive model? That's what we're gonna try to answer here with the slides and also the coding session. So what do we need? So we need, of course, the training data set, the training set, right? It could be any data set that you're interested in or whatever problem you're working on. And typically you have like the rows, right? The rows are referred to as examples, data points, data instance sample. You see all these different things. We just don't have a standard way to refer to these things. People maybe have influence in statistics. They refer to it as something else. So it depends on where your background comes from. You always have people referring to rows as different things, right? But they're referring to the same thing. As different names. So data point, data instances, and you see that books actually is not really consistent as well. You have different ways of actually referring to rows. And the dependent variable is called the label or target, right? That's what you're targeting. This is why you want to build a predictive model to actually do some inferencing and actually predict label or target. And independent variables, as we said, are called the features and covariates in some cases as well, right? So if you come from statistics, you may know what the covariate is, but if you're just working on, or maybe just beginning to learn machine learning, you'll most of the times you will hear people refer to as features. Right, some notation here, very simple. N denotes the number of examples, right? I think that's quite obvious. How do you index into data examples as you code? Maybe this it's not so important, but I think if you want to understand most of the equations in the book, you probably need to understand this at the beginning. So the superscript is just indexing into a data example, and what you see here is you have different features. This is actually a vector you see in bold, right? X on the left. And here you have the different features like in an array, and then you have this like transpose, and that's just like trying to format this particular feature vector in a columnar sense, right? So put it like in a column. And once you have it, that's kind of the ideal way on how you would feed this data into a model. So that's why you see this constant notation here. Corresponding labels, this is just the Y. Notice how the Y has also the superscript, and that corresponds to an example as well, or a sample, a data point, whatever you want to call it. And what's a linear model, right? So I'm just picking the bits that were important from the book, and I think this is the beginning where they start to discuss on the linear model. And again, remember the linearity assumption, right? We have this target, and the target is kind of obtained from a weighted sum of the features, and the features you notice here is area and age. And of course, you can see that we have these W's here, and these are just the weights, and we also have a B, which is the bias. So if you look into some other books, maybe the deep learning book from, I don't remember the author's name, but I know Ian Goodfellow is one. This stuff is discussed more in depth. This is a great reference, and I actually provided that link in our repo. You can read more about what these actually mean. So the weights, just basic idea is that what's the influence of this particular feature on actually making that prediction, right? How important is this feature to make that prediction, to get a proper prediction here? And the same thing with the bias. So the bias is a little bit different. Imagine that some cases maybe, but it's kind of rare, as the book explained it. Some things maybe there will be an output of 0, and you don't want that. Maybe you could have some kind of random value here, something like that you can actually feed to this B, this bias. This becomes your bias term, as opposed to just leaving it as 0. So that's the idea of the bias. And then all this what I'm talking about here is also referred to as an affine transformation of input features. All this operation that's going on right here. Okay. All right. So what's the goal? Now you want to choose weights and bias. These are your parameters. Do you want to estimate these parameters and right, such as on average, your predictions of the model fit the true prices observed in the data. So we're trying to kind of create an estimate, right? And we have our reserved data, right? And we want to fit it, okay? So we're going to talk more about this in the coding exercise and the coding walkthrough today. And what does this mean actually in code? Because that's the important thing, I think. And again, obviously, this is dependent on that affine transformation that we discussed in the previous slide, and that's chosen by the specified by the chosen weights and bias. Of course, weights and bias are important. So we have our, we have here the weights, the features, we have the bias as well, and that is used to make some prediction. So the question is, how do we determine the weights, good weights here? And that's the whole idea of neural networks here in this book, right? This is going to give you a method to actually come up with these parameters and learn them. And the compact form, of course, the book introduces this one here. This one with of course, you go from here, you vectorize things. They will look a little bit different. The notation changes a bit. Notice the X here is the vector, and then we have W as well represented as that. We have some transpose as well. So there's a little bit of a detail here, which is important when implementing, but these are all like to take advantage of, right? This is from a mathematical standpoint, you don't really need to worry too much on the notation here, but when you're implementing them, you make sure that you actually put the right matrix in the right place. Otherwise, Python is going to complain, and that's really important. That's why it's important to understand this. Right. So now this one in particular is just talking about, say, a particular example, but you want to work on an entire data set, so it's going to look something like this, right? So features of the data set, X represents that matrix. It's going to contain all the features, right, of the data set, all the examples. And so notice how the notation changes as a little bit. Well, not the notation, but the formulation here changes. We're doing the same thing, but it changes a bit. And we take advantage of vectorization to actually do that, and that's the idea. So at the end, the goal is to find the W and D, those parameters, right, such that for a new example and its label, the model makes the prediction that produces the lowest error. And I start to introduce this idea of lowest error. What does this mean? So we're going to talk about that shortly. Right, so we have formulation, right, on that entire data set. We know how it looks. We kind of slightly mentioned the linearity assumption as well. That's what we're using to create this predictive model, and we're depending on that. But we need a way to actually measure the quality of this model, right? Measure the goodness or badness of the model. And we also need a procedure to update and improve the model quality, because this is going to be, of course, a learning procedure. So how do we actually achieve these two things? So we need a loss function and we need the optimizer. You may have heard about these two. That's the role they play, right? One for measuring the quality, and one to kind of have a procedure, a really reliable procedure to update those parameters and try to improve the outputs of those models. Loss function and the optimizer. So let's talk a little bit about the loss function, and we're going to get into more details as we run through the code as well. But this slide is just giving you some basic idea of what it is. So the idea is this objective, right, is a function that quantifies the difference between the real and predicted values. So you have an actual, you observe data, and then you have whatever the models predict, right? Then you want to quantify that difference. So you can see here in the figure I provide. So you have this kind of the straight line going across. And you can see that there's some observation. There's also some estimation as well, right? Estimation, whatever the model learned, and how far that is away from the observation. That's going to be the difference. So how do you actually calculate this, and how do you quantify it? That's what you're interested in. And so the idea of the loss function, right? It's the smaller the value, of course, the better, right? The smaller the value of the loss, the better. And one of the popular functions, particularly in linear regression, is the squared error. Now we'll talk about how do you actually implement the squared error. It's quite simple, actually. It's just taking the estimation and observation and calculating the difference and doing a square on that. And you can see the equation here, right? You have the equation, you even have this term here. And obviously, when you take some derivative, we haven't spoken about derivative yet, but that's a topic maybe that we're going to cover later on. But when you take a derivative, actually, this will be really important to understand derivatives, because it's going to be the assignment for this one, for this particular session, after this particular session. But you have this kind of squared here, which kind of this half here in the component, this term actually cancels out when you take the derivative. And we discussed a little bit about derivatives. You start to see what role this plays and why it's important to understand it. Because obviously, if you don't understand derivatives, at least the basic rules, you don't know what the hell this is. Why do we even have this term here? But this term is just for convenience, right? What you see in the brackets, we know what that is, right? It's just a difference, but that term cancels out. You take the derivative. So that's why it's just for convenience. Sometimes you see a lot of this happen when you see this loss functions. There's always kind of a term that needs to be canceled because it favors you. Okay, so we also here is showing you the average loss on the entire data set. Okay, so you can see here everything put together. It looks like a really long thing that is confusing, but actually it's not. So you can see here how we went from the predicted value, which is y here, right? And we are doing it for each sample. You can see how here we have I is equal 1, that's for each sample, n is the number of examples, that's how you would say, and you have the summation of that. And so you have the entire loss for entire data set, on the entire data set, the average loss on the entire data set. Okay, so the average, obviously, we get it from the 1 over n, because n is the number of examples. So you can see y refers to this, right, with the linearity assumption that we discussed. And then we have this kind of y here as well, which is just the actual data, the real value. Okay, so you see the terms here again. And when we take the derivative of this, obviously, remember last week we discussed a little bit on why we do the derivative, why that's important. Obviously, when you're learning the parameters, and you need to take a derivative of this loss with respect to the parameters, and that's where you start to pay attention to those little terms over there. Okay, and I think, let's see what else I wanted to say here. Just discussing a little bit about the notation, just trying to explain to you that, just pay attention to that when you see it. This is the way you would understand it, what the superscript means, and so forth. And this is very consistent across the book, as I've noticed. Right, so you have our last function, and what we're doing is just we're training this model. We're looking for those weights and bias, right? And we're going to talk a little bit about how you actually look for those weights and bias, so what kind of principles you use. Shortly, we're going to talk about that. But the idea is once you have those parameters, those optimal parameters, you try to minimize the total loss on all the examples, all the training examples, and that's just what you see here in the equation. But don't worry about that too much if you don't understand the notation here. It's quite okay. This is just more like representing in a different way what we had here, in a more compact way. Let's see. Right, optimization. What is optimization about? Well, we need an algorithm, we need a procedure. We have our loss function, we have defined it, something reliable for this particular model, but we need some optimization procedure. And this is when we start to talk about the optimizers, the gradient descent algorithm, and variations of the gradient descent algorithm as well. So we have many books out there that actually discuss the benefits and advantages and why we actually needed to introduce better algorithms for this. And the good thing is that most libraries today, like TensorFlow and PyTorch, they always have implementation of the latest optimizers. This is a very important thing. You always want to have optimizers that are fast, always gives you, always improves the speed of the model and how it's trained, right? The efficiency of the model. So this is a very important part, very important component of training neural networks. I'm not going to go through all the details here on the slide. I'm going to share the slides later on. You can take a look at it, but this is just like my summary of what the optimization procedure is all about, what it does. But one important thing here that I wanted to emphasize on is that we had the gradient descent algorithm, of course, to actually use this one, right? We have to actually put this operation on the entire data set, which could be really, really expensive. And so that's why we introduced this idea of mini-batch stochastic gradient descent. Right, when you have the entire data set, you could get the results that you want in terms of the parameters that you're learning. It's good, right? But in terms of how efficient it is, but maybe how fast it is not the most convenient one. So we needed like something better than that. And so that's why we introduced the mini batch, which looks at mini batches and take faster steps, right? But obviously this one obviously has some drawback as well. You can read into books that explain what are the drawbacks, and there's so many other variations as well. We won't be able to cover all of them, but yeah, they achieve basically the same thing. It's just one of them is more efficient than the other, depending on the setup that you have. You may want to consider one over the other. And there, of course, I shared a link the last time on optimizers. Someone wrote a blog post about it. Hey, take a look at that reference and discusses all of these things and advantages and disadvantages. All right, so we have the procedure, we have our last function, we discussed the linearity assumption. This one discusses more a little bit about the mini batch and how it works. So at the end, our objective is to kind of have this predictive model that does well on the predictions, but in this process, we are looking for those parameters as optimal parameters. And in order for us to actually get those optimal parameters, we actually have to do what's called the backpropagation, right? So with the backpropagation, we start to learn a little bit about partial derivatives and what role they play in this learning procedure. And I just pulled this equation directly from the book. And this is how the parameter update is done using the mini-batch stochastic gradient descent. So I just put a little bit of notes here, what they are. You have to go into the book, obviously, to get the full explanation. But I just wanted to highlight some of the things that this equation in particular is what this is doing. So we have, the learning rate. The learning rate determines, how fast this algorithm should actually learn, right? Determines the rate. And obviously that's the partial derivative over there. And we explained the loss function previously as well. You can see what is there. You have those parameters being the what we are going to calculate the partial derivatives with respect to those parameters, right, on that loss function. And then we also have the mini batch size, which somehow becomes kind of like a normalization factor here, and you can see it here. And then obviously once you have that, then this is what you will use to update those parameters, right? So you have your old one, you minus that, and then you have your parameters here, and you keep improving them through some procedure. And this is what the algorithm briefly does, like initialize the model parameters. This is done typically randomly, and then you have sample the random mini batches, and then you update those parameters in the direction of the negative gradient. And if you really don't understand this statement here, update parameters in the direction of the negative gradient, that's actually going to be the assignment. And one thing I would suggest to you, I could talk about this one. I could give you examples, right, and how it works. But I think what could be really useful as a research exercise for you, and just go online and try to research. There's so many different people that have implemented, that backward function in PyTorch, implemented manually. I've actually done that as well. I've provided some notebooks for that in the past. But it's quite important to understand how to implement it, how to actually implement it manually, rather than just using that backward function that's provided by PyTorch. So try to understand what it is, because it tells you, right, it's gonna show you how to actually come up with the gradients and how to do that update on the parameters and so forth. So use those equations to actually guide you. But I think you need to do extra research. So I really want to encourage you to do additional reading and additional research, and try to come up with, try to implement that backward function in PyTorch. And I will show you later what I mean by that. But don't worry if you didn't get that now. So a lot of text here. Will not go through this one. I just wanted to spend some time on the slides, but all of this stuff is already in the book. Just want to highlight some important points. But of course, the learning rate, that's a hyperparameter. There are more hyperparameters which we'll discuss. But yeah, this one, yeah. So the most important point, obviously, the point is that if you look into the book, it explains to you a little bit on the maximum likelihood estimate principles and how we actually use those principles to get to something that's called the negative log likelihood, which is, our last function. That's where we're gonna use, and it's a very, very important part of training neural networks, and coming up with good predictive models. You really need a good loss function that measures the quality of that model. But it's really good if maybe the book doesn't explain too much about the principles here, but if you open maybe a probability book, this topic is discussed, statistics, probability. If you go into those books, those books go into really great detail on what this is, right? This is a very important part of building predictive models, and explains to you the principles there and how do we actually get to negative log likelihood. And that's what we want to minimize at the end of the day. But take a look into that. I think it's a very important topic. And if you have any questions, of course, if you're confused about anything, just let us know, okay? This slide is just showing you, of course, a lot of people compare this one is just a linear neural network. Just you can see one neuron there is the output. That's the one layer, right? One neuron layer. And then you have on the right what's the biological neuron, what it looks like. But personally, I don't really like this analogy. I don't think this analogy has anything to do with with neural networks. I think it just deviates deviates what neural networks actually do and what they're good at. And so that's personally why I don't like this analogy. But the book offers you a little bit of context on why that comparison. Some people at the beginning, at least, decided to talk about it and make that comparison and try to kind of hype things up. And well, it's your choice if you really want to believe it. But I think at the end of the day, I think it doesn't really help the discussion and being able to understand these things. It actually confuses people, from what I've seen. Okay, and the classification. So we did linear regression classification. I just have a couple more slides, so bear with me here. Classification, right? So aiming to predict a set of categories. Either it's a hard assignment or soft assignment. So the hard assignment is just classes. If it's soft assignment, in some cases you are really more interested in the probabilities, and we'll talk about how you actually come up with those output probabilities using something like a Softmax function or something like that. But yeah, those are the two variations that you have. And we want a model, right, that estimates, that's the goal, we want a model that estimates the conditional probabilities without possible classes, right? And the model should be able to output multiple outputs, one per class at least. And here's the ultimate goal here at the bottom, which is to get those parameters, to get the optimal parameters, right? Produce the proper probabilities that maximize that likelihood or the probabilities on the observed data. Okay, so that's the idea, and all of this stuff is just like repetition. It's more like a compact summary of everything that I've discussed in these slides. And one approach, of course, is softmax regression. We'll touch into that in the code. And so 1 or 2 slides here on softmax regression supports classification, binary multi-class as well. The idea is just to have the softmax functions, which gives you really nice properties, and right, they meet some desired criteria. And so when you're outputting, like when you actually get the outputs directly from the, using the linearity assumption, the WX plus B, whatever that you saw earlier, those give you the logits, but those logits, those values, they actually come in a way that doesn't really they don't have the criteria or the qualities that we want. So we need something else. And we need to transform those into output probabilities, right? And so we have this idea that we want to meet these desired criteria. So we want to make it non-negative. We like non-negative values, right? When we're working with predictive models. So that's why we have this non-negativity. And the way we get this non-negativity, if you look into a softmax function, is just that you need to do some exponentiation with some values. And once you have the exponentiation, it gives you that non-negativity. So that's what you see this softmax function. It has this exponentiation function in it. It has to be differentiable, obviously, because all right, we want to learn parameters, right? We need to on model that is able to backpropagate that result that we get and try to learn those new parameters using that procedure that we discussed earlier. And so it needs to be differentiable, right? And some functions are not really differentiable. But this one in particular has that desired criteria of differentiability. And also, if you're building a predictive model, you really are interested in those probabilities and that they follow that criteria as well. Some specific distribution. So in this case, you want them to sum to 1, right? That's just following at least they follow the axioms of probability. This is what we discussed in the previous lesson. So that's actually a very important thing as well. So we have those nice criteria that we're meeting here with the softmax function. But obviously, originally, softmax function wasn't really used in this context. It just happens that it has those really nice qualities, and you know, they were adopted in neural networks. Okay, so and then eventually, I think one very important thing as well with the cross-entropy loss, we had the loss for the linear regression or for classification problems in general, and actually very common. We use the cross-entropy loss function for classification problems. Right, so the same idea, right? We want to do like, so we have like we want to measure the difference between the two probability distributions, right? And that's going to give you a measure on how good this model is actually doing on the particular task. Yeah, and that's what this one is explaining. And if you really want to understand more, I would say take a look at least at that segment that's information theory. Don't jump, even though it's not really highly like connected with deep learning and so forth. But just understanding that bit of information theory and you know how the cross entropy loss is related to this and what it actually measures, I think is quite important. Right, so the assignment is going to be this one for those of you that are working on towards the certification. You will have a background function. I'll show you which one it is that you have to work on and implement. Please, for the linear regression part, you don't need to do it to the softmax one. But for the linear regression one, I think should be easy to implement. But the idea is to encourage you to actually do research. I mean, when I was actually learning about these things, I remember that was the first assignment. The first assignment was go and try to implement backward. I was so upset. I mean, I didn't even understand like the equations at the beginning of what they were doing and but just going through each step and trying to understand and trying to code it myself, I got a better intuition of what it was. And I think that was such a wonderful experience because it pushed me to go into all these details and try to understand it myself. If I were to give you a solution, which I will do in the next session, I'll give you my own solution. I'll talk about it in terms of code. You know, I don't think you will get much from it, and I think it's such an important part of training neural networks that I think if you want to dive deeper, you really need to understand this concept. All right, so that's going to be the assignment. It's an individual assignment, and right, so you would have, I think maybe 1 week won't be enough. I'll try to give 2 weeks for this one. I'll put the deadline. I think 2 weeks should be enough. And I'll provide a solution for you also, not probably next week. If I make it 2 weeks, then I probably won't give you next week. I'll try maybe move it onto, it depends on when the deadline was, but try to give me some feedback on that, whether 1 week will be enough or 2 weeks, or you need 2 weeks. It depends on you as well, but I would like to give you 2 weeks. I think it makes sense to give you 2 weeks. Okay. So let me know in the chat, in the Slack group, if that makes sense. And if you think you can do it in 1 week, then we can do it 1 week. But for now, it stays at 2 weeks. You have 2 weeks to actually complete that. All right, so, okay, we have a demo now. Okay, how do I escape this? Okay, connect. All right, so let's jump into this one. So this is a coding walkthrough. Let's see how much time we have. We already did 45 minutes. I don't think it's going to take more than an hour, to be honest. I think it would take less time, but let's see. Oh, there were so many questions, right? Many comments here. Okay, let's see. Okay, so yeah, taking the average of endpoints. Thank you for that, has one. That's a great answer right there. Someone was asking about what the 1/n stands for. Okay, just checking to see if there's, right, let's see. Okay, most of them were comments. All right, let's move forward. Right, so linear, let me just try to expand this a bit. I think the most interesting part is obviously the code in the book. I really love the code segments. I don't know what's your experience on it, but I really love it. I wish I had resource like this to actually learn these concepts. Not everything will be explained, that's expected, but I think you have to do your part as well. You have to go through certain things yourself and try to get better intuition at least, but the book really does provide a good foundation for training neural networks. So that's I think most of you, that's what you want to learn. All right, so this notebook I will share later because this will become the basis for that assignment. So you can actually, there's a segment where I say it's an assignment, and for those of you that are interested in completing that assignment, I really challenge you to actually try it and see if you can get it done. These are just the libraries, right? We have the D2L, there's a particular library for that accompanies the book, which is great, has some good functions that we can reuse. And obviously this is MXNet, but yeah, we need to install MXNet to actually make use of those functions. These are just, let me just go through this really quickly. These are just the libraries we'll use throughout, right? NumPy, there's nothing unfamiliar here. The math is just a math function. To get our math functions, our time, random, and NumPy as well, kind of use that as well here. So yeah, I discussed a little bit on vectorizing and how important that is. Actually, if you go through any, I think for most popular machine learning courses that I've seen, or deep learning courses, there's always this chapter where vectorization is explained. It's quite an important concept to understand. And when you see an equation, how do you actually implement it? Most equations, probably already are in their most optimal form. So you can definitely leverage vectorizations for any of the toolkits you're using to actually improve the speed. You always try to, make those parts optimal. Transformations on the data or something like that, you always want to use that vectorization capability of your toolkit that you're using. Right, so here it just explains to you some examples, right, just to show you the efficiency of the vectorization. I actually work on this. I had this notebook prepared from, I think, last week. So hopefully I remember every section, but I just kind of, just to say that again, I always forget, but obviously all the credit for this material goes to the authors of the Dive into Deep Learning book. Obviously they are contributors because people are actually contributing this PyTorch code and so forth. Right? Nothing here is originally done by me. I just kind of adopted the code, and we have permission to actually do that. So I always want to say that in front of, that's really important to give people credit where it's due. All right, so yeah, so some examples here we have, right? We discussed what the ones, torch at once does, and we have A and B, and how many examples we want. It's 10,000. So we have these matrices right here, and A and B. And I think this, yes, this is a really neat class. Usually you won't see this, you don't really need to implement this, but I think it's quite useful. And I like that they actually implemented this. It gives you some really nice functions here to set up a timer, right? So you want to know how long code takes to run, you can actually just leverage that. And here it creates a timer with the timer class. You have a timer object here, and you can actually easily check how long a piece of code actually takes to run. And here we see that for loops are not our best friends when you're building neural networks and models. So we have for loop here, but ideally what we want is we want to implement, do the same operation here, which is just adding components of one, I think, a vector to another, right? And then assign that to this additional one, which is C. And here we're doing it individually, right, for each of the items, and we're iterating over each one of the items. But ideally what you want to do is you want to do something like this, where you could just go A plus B, and we talk about how efficient this is, right? And then how those toolkits like PyTorch and TensorFlow actually implement those and give you those capabilities to actually just go ahead and do this sort of operations like this, rather than iterating over each item. That's not the most effective way to do this, or efficient way to do that. Okay, so take advantage of those reloaded operators here, and this one just does an element-wise sum. We discussed that in the previous session. And let's see if I run this. Actually, let me run this one first. Right, so you see how long it takes. And by the way, this is not a really huge vector, but you can see this one took 0.12 seconds. And then this one is like 0.0003 seconds. You see how efficient it is. And actually, as you add more examples, those data structures right here, this actually, I think, exponentially takes a longer time. So just pay attention to how efficient that is, and try many different examples to get an idea of that. But this is becoming more easier. This is the reason why the last time I discussed the profiler, I think the profiler in PyTorch makes a lot of sense in particular, but other tools actually have profilers where you can actually kind of diagnose this and get an idea of what parts need to be improved and optimized. And so maybe you have a for loop that is unnecessary there, and those tools can help you figure that out as you practice how to build neural network models. Okay, so an implementation from scratch with linear regression. Let me just take some water here. Okay. Right, so this is a implementation from scratch. So we have the data pipeline, see how the different parts, and then the modeling, then the loss function, then we have the optimizer, right? The optimizer is the procedure that we need to actually train this model. And we have a data set. Let me see if I miss anything here. Okay, so we have a data set here, right? An artificial data set is generated, follows some Gaussian distribution, normal distribution. And yeah, this is what it's doing. It's rendering some synthetic data. You can see here your X, you can see here your Y. X is just, I believe it's a matrix. Yep, and then, this, right, the transformation, right, the affine transformation that we discussed, right? We already saw that that equation. That's what you see here. And the matmul takes care of that, right? It's multiplying matrices. You can see how you get your Y. And obviously right here, want to add this additive noise from databases, the Gaussian distribution. And you can see the book for more ideas on what this means. But this is how they actually implemented, the contributors implement this one. Okay, so return that information back, and you can see here, let me just render this. Okay, so we have our features, our labels. So we have features, then we have labels. And so if we run that right here, so we see that the feature shape, what's the shape? This is a 1000 by 2, right? 1000 rows. We have 2 features here. And then we have the labels, right? It's just one label for the 1000 examples. And yeah, so this is what this particular model, this very basic model, actually return. You can see the values there. And then the label itself, which is what's here. Okay, let's see an example. Okay, so this one is just printing out the features. Sorry, so this one was the features for the first example, and then the labels for the first example. So I got that wrong actually. So yeah, this is what it means. All right, so let's keep moving here. This is just giving you some ideas on the things that they were gonna use later on. If you're starting out, this is why I like the examples, because it really starts you with basics, and then it moves to the actual model and how you would implement it. So I really like that from the book. I think it's very approachable in that sense. So okay, here we have the figure. So we actually have a plot here, and that's our synthetic data right here. That's already plotted, and you can easily see that maybe yeah, a linear model would be sufficient here to actually maybe deal with this particular data set. So we run this one. So that's how you get this one. Okay. Oh, yeah, that was it. This is just more like examples and things that you will use further on, but there's actually a lot of code that I actually jumped and skipped. I didn't really want to cover that. You can actually do that on your own, but that's the idea. So how to read the data set, right? That's the most important thing, I think, like how to load the data set and load it efficiently. So when you're training a model, how do you actually feed this data makes a lot of, it makes a lot of difference, because if you feed it wrong, if you don't feed it efficiently, yeah, you will always, you have models training forever. And I think a lot of you have experienced this before, that sometimes we run out of memory pretty easily and really quickly, maybe because we haven't really we're not loading that data properly. That's quite important to understand as well. So this one is just creating I think a data iterator. So just creating some way to iterate over data, and it's telling you how do you actually do that in a manual approach, I think. So let me just run this one. Okay, so here you can actually get a batch. So for X and Y, using that function, you pass in the batch size, which is this, the features and the labels. And so you can see here some printing some examples, and of course I want to break it. And that's very simple code, but you can see how it's using the, so it's actually creating a sample, obtaining some samples here. And of course, our samples of batch size 10. And that's what you see output here. Right, so the note here is that it's an efficient implementation because we're doing a lot of random memory access. That's the most important part here, because as you see here, we're iterating over each one of those items and trying to figure out our batches and so forth. And this is how it typically was done. But the good thing is now with tools, you have modules that you can take advantage of and to actually set up your data iterators and actually set up your mini batches, which is what you will mostly spend time on. And we have tools that actually take care of that for you. And PyTorch in particular is well renowned for that. There's a lot of functionality for this, for actually setting up your data loaders. Okay, so this code is quite simple. This is the I think initialize model parameters. How do you initialize them, right? So you want to sample random numbers from the normal distribution, and it means 0 and a standard deviation of 0.01, and that's how you would specify it. And yeah, and set the bias to 0. So here you see zeros, right, with B. That's our bias. Okay, so we initialize our parameters, then we are ready to, so we loaded our data, right, synthetic data. We have initialized our parameters, then we define a model. This is a very simple linear regression model. You can see here the operation that's going to happen, right? Multiplying these matrices X and W, and then we add the bias. That's a pretty, that's the most simple one that you will get, right? And that's your linear regression model. So let me just run that once more. Okay, so let's see. And then of course, you want to define the loss function, and the loss function is this squared loss. So you can see here we have our y hat, which is what we're predicting, the model is predicting, and we actually have the real labels, truth, right, the ground truth. Let's see y and y hat. So we have this one being the ground truth, right? So we do the squared loss, and let's see. Yeah, so you can see how it's here. We divide it by the half. Remember the half, so we're dividing it by 2, and we're squaring that. Yeah, that's right. So that's a good implementation. And we have the optimization algorithm, the SGD, right? So we have, so this one, what's happening here? So just using minibatch stochastic gradient descent, we are going over all the parameters of the model, right? So, and for each parameters, we're kind of doing some update, and this is what we're updating it by. If you look at the equations given in the book, that's actually what's happening here. And so we have this kind of normalization as well. This is just to kind of remove that dependence on the batch size. So that's why we have this batch size here. But ideally, what you don't want to have is just something like this. But again, this is just a small detail. And then you want to set it to 0. Okay, so once you have updated your parameters, you're going to the next round. It's important to actually, reset those, because we don't want to like accumulate those results. We just want to, like, every round we want to set them back to 0 or reset them. I think that's what it's, yeah, that's what it should do. At least the gradients, right? But the gradients is what we're focusing on here. All right, so let's see. Then we're ready to do some training. We initialize the parameters. We did initialize the parameters. And so now we are computing the gradients, right? So once we compute the gradients, then we update the parameters. And how do we compute the gradients? That's the thing. Notice here we just use this step here to actually just update the parameters. But actually, that's skipping the step of computing the gradients first. We need the gradients first to actually do. So you can see here parameters are grad. That's the gradient to actually do this update. But where was that done? And that's actually the assignment that I was talking about. So here we see that we're leveraging this backward, right? This backward function in PyTorch, which actually computes the gradients for you. Computes the gradients on the loss with respect to those parameters. So that's what you see here. That's why, you know, even though it does it for you efficiently and everything, I think this step in particular is quite important to understand, at least at this part, at this phase of the study group. I think it's really good to know those details, right? And that's kind of the assignment here. Just make a clone of this notebook and implement that backward step and basically reuse the same code. So you can actually just go ahead and once you have implemented this function, take a copy of that and just try to insert it here. So you can actually reuse this. I'll share this later on. And that would be the assignment. So let me know if you have any questions on that. I think this should be a quite simple one. But the idea is if you don't really know, just try to do some research, push yourself, and try to. There's so many people that have done implementations about it. It doesn't really matter if you go and try to study some code, but please just try to understand it. Put some proper comments and what's your understanding and your intuition behind what the backward step does. But I think at this stage, it's important to be able to implement it manually, but later on, this stuff, you don't really need to worry about it. All right, so that's the idea. We have a square loss. This is just the loss, right? This is just the function square loss. And yeah, so we do, we run it for a couple of times at your epoch. In this case, 3. And let me see if it works. Oops, I think I missed one. What is it that I missed? Square loss. Yeah, so I skipped this one. There we go. So this should be working. Now we set up a learning rate. Feel free to play around with the learning rate as well. But you can see here that the loss is decreasing, and that's ideally what we want, right? So in this setup, you can definitely, claim that the model is actually learning something and it's actually doing well, even on this kind of synthetic data that we kind of pulled together here. Okay, so let's see what parts I wanted to explain. This is just the SGD. So we have, so I think this one in particular here, this LSUM, where we're doing some summation here. When we actually use backward, this is not very common, like to actually do a summation and then do a backward. So later on, I think there's an example where this is simplified even further. Okay, so we're going to look at that as well. And the problem is that we are actually building our own loss function, right? So because we're building our own loss function, we had to do something like this. But ideally, what we want to use is a loss function that has been implemented for us. And of course, in PyTorch and tools like this, you already have that implemented for you, so you don't really need to take care of that. It becomes a lot simpler to actually do this. And of course, here net is just our linear regression model, and this is the standard way of actually defining a model. These are just the things that you're passing to this function, which you have implemented linear regression right here. And then it outputs that for you, and it calculates the loss. I pass that to the loss function, calculates the loss, and so forth. Yeah. And then that's the assignment. I discussed that to you already. If you have any questions, let me know. I'm happy to answer anything that you want to know. But challenge yourself, please. Try to figure out how to implement it. I'll give you a solution, the next time when we meet. Okay, so this one is, let's see. Okay, this is just comparing. Okay, yeah. So the true parameters are the ones learned. So we actually had some true parameter. I think we defined that somewhere. I think I skipped that step. Where was it? True params? Where was it? Trying to figure out where true W. So we have the ones that we learned, but we actually had the true W and true B, and then we kind of estimate the difference, and we can actually see that they are quite close, right? Even for a simple model like this, we actually got the most. We got very close to the most optimal parameters, but I don't know. I don't remember where that was. Let's see if I find it. Oh yeah, here it is. Right, so we have our true parameters and so forth for generating that data. So we actually had it here, and I forgot to talk about it, but that's what we used for the synthetic data. Okay. And we learn those parameters, and you can see even with a simple model, it comes quite close. And we will never actually get the perfect parameters that we want, because obviously we are kind of sacrificing, or we're kind of doing some trade-off, right? And we always do this trade-off when we're training models, and that's why we never can get the most optimal one, but we get really close to it, and that's something that is guaranteed. Okay, so concise implementation of linear regression. So now this one was from scratch, right? Even though it claims it's from scratch, it's not really from scratch, because I think this is the most important step, which this one leverages the functionalities in PyTorch. But I think if you can implement that function on your own, I think you're basically very far away, far into learning about about deep neural networks. Very important step. Okay, so linear regression or concise implementation basically is just the same code, I guess. I'm gonna read the data sets. Oh no, so this one is new. I think really important. Again, reading the data sets. How do you actually load this data very efficiently? So here we have a tensor data set. If you look at this data, what is this data? Where does it come from? So it's a utility function here in PyTorch, and this is really useful. So if you look into data, if you look at the documentation of PyTorch, you'll find that there are different ways on how you can actually structure your data. Okay, great. Different representations of your data. So this one is just saying, I want to create like a tensor of this data set. And you pass in whatever data you are interested to transform. Okay, so, and then it creates what's called the data iterator. So this is a data loader, and this is another function, utility function. And then, just passing the data set, right? This is the data set that we have here. But when you pass this data set, it already has to be in this format, in a tensor format. I mean, you can have a NumPy, say a NumPy object, right? Your data could be in a NumPy format. You can transform that NumPy, say, array into a tensor first, and then once you have it in a tensor, then this data loader expects a PyTorch data tensor. So that's what you're going to pass in right there. That's why this first step is important. And then we have a batch size, and then if you want to shuffle, right? Shuffling is always good. So if you want to shuffle, I think that's good. And obviously shuffling just for the training, at least for the training, which is what we're going to use for training the model. Okay, so let's see. We have done that, and then of course we can leverage that. What you see here is the data iterator, a PyTorch data iterator specifically, and then we can leverage that, and we can start to look at samples of this, batches of this particular data loader that we have created. Okay, this data iterator that we have created, and you notice how before we actually did it with the iterating using the for loop. Well, these are your solutions right here. These functionalities, these functions here that allow you to optimally create data iterators. And if you ever skip this step, and this is how you have learned. So if you have learned to do it using the for loop, you're missing out on a lot, because these functions are there for a reason, and everyone that's an expert in training models, they use these data loaders. So definitely use them and understand how they work. That's a quite simple concept. Okay, so then we have the data, then we kind of define a model, and in this case, we're using the sequential. Basically, we're just adding layers, just layers of transformations. In this case, it's just a linear layer, right? And because it's a linear model, then we just need one of these. And that's a very simple model, and we assign that to net. That's going to be our model. And then our models, of course, we want to initialize the model parameters. Notice how different it is. We're not doing like double is equal whatever, but we are directly accessing the parameters of this model that we have just created, leveraging this functionality of PyTorch. So very concise implementation, right? So you're just doing this initialization model parameters right here. Okay. All right. So let's see. Let me run this one. And then we have a last function. So let me just take a second here to go through some questions, if you have any. Yeah, the backward function is exactly the, that's the backpropagation right there. It's called backward for simplicity, but you want to, so as I said, we saw in the example that, we show you how to update the parameters, but that's actually skipping a step. How do we actually compute the gradients, which is what you use to update those parameters? And so that's why we have this backward function that computes those gradients, those derivatives. So that's part of the backward propagation algorithm, right? So of course, yeah. So like I said, if you look into PyTorch documentation, I think you can see how they implemented this one. So that's a hint right there for you. The source code, you can always go back there and see how they implemented it. You will see something really crazy, obviously, because they are using a lot of efficient code, but just do some research around and try to understand it. Okay, let's see. Yeah, as Ars had said, calculating all the partial derivatives. Definitely, thank you for that. Right. So I think someone is in the chat. It's kind of let me try to mute this one. Oh, perfect. Okay, so let's continue. We have a loss function. Okay, so we initialize our parameters using this, right? It looks a little bit weird, but just this is your, you have a model, right? You have that weights, so this is just your weights, and you using a normal distribution. That's how you kind of initialize those weights, and the same thing with data field, just set it to 0. Okay, and then we have our loss function. So remember how we actually implemented the square loss? Now we have all these functions that we can actually leverage from PyTorch. So we don't need to implement it ourselves. And because we don't need to implement it ourselves, all the job is done for us. Remember that summation is happening. We don't really need to do that. All that is taken care for us. And in this case, we are using the mean squared error loss. And and then here, of course, we choose our optimizer, and it's just a line of code. Previously, what we did is we implemented the SGD, right? Remember the SGD that we implemented? So let's just show you that again. Okay, so we implemented the SGD, which takes care of updating the parameters using this particular. You do it in a manual way. This is not very common. You wouldn't need to do this. In some cases, maybe where you really want to tweak something there, maybe you would use this. But in most cases, you're just applying deep learning models, and you don't really care. You just want to use the latest and greatest. Once it's available, you could just do it in one line of code. Right, so you pass in the net parameters. These are just your parameters, which are these things right here. And you have a learning rate. And notice how simple it becomes. So you have a loss function, you have your optimizer, and then you're ready to train already. You haven't even actually just a couple of lines, 1, 2, 3, 4, 5, 6. This is 6 lines of code, and you're ready to train. That's just to show you how simple things are at this point in time with these tools. So we have, of course, our epochs. We have the same here, iterating through the data. And this is where becomes really, really cool to implement and have implemented, the data iterator. Because now, it's going to do all that magic for you. It's going to select batches for you. And you don't really need to care about randomization. You don't really need to, all the stuff is taken care of for you already. All the shuffling, you don't really need to do that manually anymore. As we showed you in the previous example, where we're doing that manually. But now we don't need to do that. And the thing is, when you implement it manually, not only are you kind of losing out on that efficient implementation, but you also are prone to mistakes and errors. And that's where the trouble comes. So that's why we use these data iterators. And of course, that's a best practice when you're using PyTorch. I don't know about other tools, but in particular, PyTorch, you want to leverage those things. And of course, a data loader, you can create your own class, right? And you can design it however you want. There's so many examples in the PyTorch documentation on how to load all sorts of data if you're working with text data, if you're working with image data, any sort of data that you have. All right, so the last, quite easy. Then we have the zero grad, right? And remember how we kind of cleared the gradients before? We needed to zero out the gradients. Well, here's just one call to this function, right? Using our optimizer here. And then once we have cleared that out, right, we don't want to accumulate those. That's very important. For every round, we don't want to accumulate those things. And we kind of compute the gradients with the backward function here, and then updates the parameters, the update step. That's what we saw with the function actually at the top, and it's done for you. Okay, so these 3 steps, very common. If you look at some, paper implementation, this is what you will see in the trading step. These 3 are very common to see together. And actually, tools like I try to not forget this part, which is quite important. So you may ask yourself at this point, hey, why do I really need to do these steps? Well, it's very repetitive that I need to, let's say I want to experiment with different models or variants of the models that I'm creating. So why do I really need to do all these steps over and over again? Why don't we have like a simpler function that, and even a high level function that actually does these 3 steps together? Well, the idea of PyTorch in general, what they wanted to do is just give you these functions that does these things, solve these different components of the model, separately, right? And then you have even higher level functions that does even more abstraction to your code, your PyTorch code in particular, which is called PyTorch Lightning, and that's really an amazing tool that the community is supporting a lot, and we see a lot of people trying to build content on that. I think if you go through this course and you learn the basics of PyTorch and how to actually implement models, I think that will be your next step, because how to implement models and how to actually put out experiments really quickly, it becomes really troublesome to actually have to do this stuff like all the time. So those, and how to load data, for instance, as well. This could even be further simplified. And so those high-level tools like PyTorch Lightning, they actually take care of these things. That's something just that I wanted to put out there. So if you're interested in that, please, I think I would highly encourage you to actually take a look at that library. Okay, so let me just load some code here. The loss, let's see, the trainer, and then this one. And you can see here how the loss is kind of reducing on every step. All right, so this one, okay, we want to compare the 2, we have our 2 parameters, right? And then we have the ones that we learn. And you can see here, it's quite close to the 2 parameters. So we did really well again. So when you're implementing your backward, this is the code you're going to use again to test it, right? So you don't really need to deviate from the examples. It's just that you need to implement this one separately. And even those of you, by the way, that are on the call and sitting in those sessions but are really not interested in the certificate, I really challenge you to try it out. I think that would be a really good way to maybe review something, kind of review. I think it's good. All right, so okay, so that's it for the linear regression. Now we're jumping to softmax regression, which is this is the kind of the most common one that you see today. A lot of classification data sets, right? If you go to Kaggle, like a huge portion of those data sets are actually for classification. So you always see the softmax, right? Softmax helps you to gives you some like I said, the criterias. Remember the desired criterias. And the softmax function gives you that, and to be able to output probabilities that are actually usable, and you can actually learn a predictive model. Okay, so this one we went from like 1 neuron on that output layer to we have multiple outputs now, because it could be a maybe a classifier with say 3 targets. So you have of course more neurons and taking care of that. Okay, so let's go through the image classification data set first. Again, you see how important it is, at least in the book, and I really like that from the book as well, that the book emphasizes a lot on how to load the data efficiently, because other books don't actually do this, and they expect you to learn this on your own. But I really like the emphasis that the book actually puts on loading that data set properly and taking advantage of those functionalities in these toolkits. Because later on, as you try to use say something like an RNN or something like that, you take advantage of this, which becomes even more important, because with those type of models, yeah, you're definitely working with even more expensive operations. All right, so let me load this one. Let's try to see. Okay, this one again, nothing too new here. A torch vision, right? Those gives us for those people working in computer vision, it gives us a lot of like transformation tools, right, out of the box and so forth. So torch vision, that's again related to torch. And here I'm this is a cool thing about PyTorch and why I really liked it at the beginning. I mean, this stuff was there from the beginning, I think. When I started to use the first versions, they already give you data sets that you can play with, which I really liked. I think at that time, no other tool had done something similar to what they had. And that really made it a really good learning experience, because then I didn't like, if I wanted to get started with deep learning, I didn't really need to, pick up my data sets. At that time, I think you had to like download data sets, you have to format them properly, you have to convert them into tensors, and then you have to load them properly. But this stuff is done for you, at least with some examples, the fashion MNIST, and a couple others. So take advantage of those. Actually, there are some text-based data sets as well, I think, that you can play around. So play around with that. I think as an exercise, try to look at the text-based ones and just look at the documentation, how to load them. Okay, so again, the same thing, right? With the transforms, this comes on specifically for computer vision problems. You would have all sorts of transformations that you need to apply to your data set, right? So sometimes you need to like crop it, sometimes you need to do some data augmentation. By the way, data augmentation is quite an interesting like phenomenon recently in the field. And I think, so I've made some notes on that. I think I would want to do some, and have a library that I've been using on the side, and maybe do, like maybe a portion, take a portion of one of the upcoming sessions and just show you how to actually use those things, and then specifically using PyTorch. So that's something that I'm going to cover later on. So don't worry if you don't get everything today, but I think I want to cover some more topics on that, because it's becoming quite important, because obviously data is very limited, and data augmentation helps you to expand your data sets, whatever you're working with. But here we have transforms. You just transform it to a tensor, as I said before, you actually load it using the PyTorch data iterator. So yeah, so you have this transformation function, and then here you have MNIST and MNIST, and you just load the data, right? This is going to download the data set for you, and these are just the built-in data sets. Okay, let me see if I can do that here. I think I already did it, right? It's actually doesn't take too long. Yeah, and it's done. Right, so we can check a little bit about the data set. It contains 60,000 examples, I think. It has 10 categories, I think 6,000 for each category. And we have testing data set already for us. It's already split, right? Okay, so we have the 10,000 as well for the testing. And you can check how this, for each input image, I think 28 by 28 pixels. And then, of course, this is just one example. Right, so now we're going to start to do implement some functions. So this one is just to get an example, I think, of this particular data set. Yeah, so we have the text labels, and then we can just basically try to, this function particularly returns the label. So it's just returning the label of a sample. Let me see. So let's see where this one is used. I think it's used somewhere. Let me try to see. I think it's used later, not now, but that's why I found it really confusing that it was here. But anyways, I'm just trying to follow the book. This one is just to visualize an example. Let's see, visualize an example, and then, yeah, just go through the code and try to understand, this one is using matplotlib, and there's actually some functions that have been implemented with D2L, right? That's the library that's accompanies the book. And just take a look at that, try to understand what this is. I'm not going to go through all the details here, but this is just to visualize example. And one great thing, it almost feels like, when I was writing my tutorials, I used to write a lot of tutorials because I always went through these steps. And some people ask me, like, why don't you just jump into modeling? No, I don't want to jump into modeling. I think for people to understand these tools, you really need to talk about the data set and how to actually check your data set. Even, we're used to just using data sets that have been prepared for us. But I think part of understanding these tools, and obviously because there are a lot of functionalities there, is trying to understand this way of loading the data and trying to processing the data and trying to create changes in our data as well, if that is the case. And so I really like that also as part of this book, that they encourage it using these code snippets. They didn't really need to do all of this, but I really, really like that they do it. And this is it's the best practice, in my opinion. So now we look at the data set. It looks okay. You can see here ankle boot, t-shirt, dress, and so forth, right? You see the labels and you see the actual sample. That's your, and we're using the data loader, of course, right here, right? Notice we passed the empty string and the batch size. So that is what is expected from the data iterator, which is just this data loader function. Then we show images is just this function. Cool. Now we know we're working with the right data sets. We know everything is set up right because we have the labels and so forth, corresponding labels for each of the images. And this one is just like, you can actually simplify this further. You can just, of course, loading the batches. That's what you're interested in before training the model in this data set. And there's this really, so I shared this article here. I think it does a really good job, more so than I think the documentation itself, but it does a really nice job of explaining to you what this is with the number of workers, right? So you want to, if you have access to, many CPU cores, so what you can actually take advantage of that and set up a couple of worker processes and then try to, load the data even faster. So that's what I was saying, that there are all of these different things that you can tweak and you can optimize. And PyTorch makes it really easy for you, right? It really gives you the functionalities that you need to make it, to load your data much faster, which is an important part of training the models. So take a look at that article, highly recommended. When I shared the notebook, just go and read it. Then of course, just a timer here, and then just checking how long this takes to load. Remember, this is like, okay, let me just, before I forget. So this is a 60,000, 70,000, data set, contains 70,000 images, and look how fast it loads. I mean, if you are trying to do this manually, it takes a while. Okay, so we want to load the batches. Then this is another function. Notice everything goes into a function, right? We want to separate all these things. Load batches, we want to do all that. In this case, we're maybe doing some transformation. Notice we're kind of, the transformation, remember the trans was more like transforming this to a tensor. And then, of course, you use this transform compose. So let's say we had a lot of more transformations that we want to add. So apart from converting it to a tensor, maybe we're doing a rotation, maybe a cropping on the images. This is the sort of things that you actually work on when you're doing computer vision. So all of these things will go here as part. So this notice is an array, but you can actually have more transformations. And obviously, PyTorch, given that they already implemented something like this, they give you some built-in functionalities for this, which you can actually customize your stuff as well. And you can see another example here, transform resize, right? Resize, just resizing the image. So that's you can see really, really great stuff, really important to understand. Okay, so load batches, and what else is here? That's just loading that data set and then return the data loader, which is the data iterator. You can see how many workers we're using, shuffling the data set, creating a different batch size. And you can see that we created a data loader for each one of our training and testing data set, okay? So once we have that, then we can iterate over the training data set, and we can just print it out to see if everything is okay. I think I missed this one. So you can see here that it's checking just for one of the batches. So we have batches of 32, and they're by 64 by 64, I guess. Yes, yep, that's right. Excellent. So, yeah, notice this parameter resize 64. How did we actually achieve that? Well, we pass it to this one, and then we use this one and we resize. This stuff you had to do manually before, but now, good thing you have those functionalities which you can actually use directly. Okay, so let's see. And then we have implementation of Softmax regression from scratch. So that was more like more data loading, right? Spend a little bit of time on that, but we know everything is okay, our dimensions are okay, and now we are trying to implement the model. And then here we have, let's see, okay, batch size 256. And then, so that's gonna be our batch size. And then we can just load that function, load data fashion mlist, provide the batch size, and it's gonna give you those data loaders. So this function that you see right here already comes part of the D2L package. So you can just use it directly. Okay, so let me just load that. And then, so your weight matrix, right, with the additive Gaussian noise. So we have inputs, number of inputs 784, right? That's gonna be, so how do we actually end up with 784? If you actually do a 64 by 64, that's gonna give you 784. So that's gonna be your input, right? So it's just gonna be like this column, just visualize it as a column, and that's gonna be the number of features. for that input, for each input. Okay, so the number of outputs is going to be 10 classes, weights, and so we have our weights, and then we have our. So one thing I didn't see here, which maybe I can also do later on. I think when you're implementing these models, there are many ways you can actually do this. Like, I think it's better if you do it in a class, but here I see that they just put it outside like this. I think we maybe want to use some class for this one. But anyways, maybe later on I can show you, or maybe the examples later on actually have that. If they don't, I will adopt that because I think that's another kind of best practice as well, trying to set these things up in class. They're much easier to work with, and you have a lot of more things that you can take advantage of. All right, so let's see. We have weights, biases, then okay, and then so we have a softmax operation. Let me see. Okay, so now we have our data. Let's see what we're doing here. Oh, so we just wanted to test. So we have an X, and then and just showing you like what the I think the operation is, right? So it's just telling you when you do a summation. We went through this the last time. So when you actually have 0 or 1, how is this actually summed? Is it sum by column or by row? So it's just showing you that. In the first example, of course, if you see it's taking X, so it's going to take all of this, right? These two arrays, and it's then going to use the 0 axis. So it's just going to do it right by, I believe it's by column. Yeah, so it's going to be 4 plus 1, 5, 2 plus 5, 7, 3 plus 6, 9. And then, so they show you this example because, when you're doing the softmax operation, there is a summation involved. That's your normalization component of the softmax function. So that's very important. So it's right here. So this is a softmax function right here implemented manually for you. But obviously there's, you can actually use the built-in one as well. But this is implementation from scratch. So they're keeping their word. So we have the first one is the exponentiation. If you have seen a softmax, let me see if I can actually pull that here really quickly. Softmax function. So what are we doing here? This is exactly what we're doing. We have this kind of exponentiation that's going on here, and then we have a summation at the bottom. So that's exactly what we are implementing. Oops, sorry. Okay, where is it? I'm lost. Here, right? So we do the exponentiation first, then we pass that, and we do, now we have the exponentiation, we do a summation on that, and then we actually do a division, right? So that's what we see here. And all that broadcasting stuff is actually being applied here. So for each one of the elements that you get, there's, right, so there's some summation that's going on. So let me show you what that looks like. So if you have an example down here, so look at this tensor right here. Let me just run it first because the example changes. So this is a tensor, that's your X, right? Normal distribution here. We're printing it out. Then we have a softmax. So what does it do? So if we have something like this, imagine these were like 2 examples, right? So 2 examples. So you have many values for these arrays. These are just examples. And then you maybe wanted to take, apply the exponentiation function here on that. And so how does that look like? Well, let me just show you. So I did a printing out. That's how you understand this stuff. So after you print this one, the original one, which is this, right? And you take this, of course, after you do this one, what do you get? So you get the same, right? Nothing changes, the dimensions stay the same. All you're doing is just taking exponentiation of each one of the items in X. That's what you see here. And then it says, do a summation on 1. So what does this mean? Well, it's going to do a summation this way, not this way, right? So we say if it's 0, it does it by column. If it's 1, it does it by row. So it's just going to do reduce it that way. And then that's what you see here. So we have those values. That's what we do to get the final result from the softmax function. And what's returned, we take this one, which has been exponentiation, and divide it by the partition part, which is the summation. And you get back something like this. Okay. And if you sum them, right, these are probabilities. If you sum them, they should sum to 1. And so these are all like sanity checks that you can try and then just to make sure that everything is going okay and your implementation is right. Okay, after your softmax function, we have that. So I think it's time to define the model. And the model is, of course, you pass that you know, or you do a math multiplication, right? So you have your x, and then you have your w, and then you plus it by b. It's the same thing, right? It's just the kind of your linear layer, and then you pass it on to the softmax function, and it outputs the result that you want there. Right, so the cross-entropy loss, what is this about? Okay, so this one is a loss function, right? So we want to implement that as well. So where is that implemented? So this one shows you some basic examples of kind of the operation similar to what you saw in the softmax function. So what's going on with this cross-entropy? How do you actually get that? So you can see here is an example. So we have a tensor of, you know, with two elements. And then if you wanted the y hat of that, sorry, so this is going to be your y hat. And then, you know, if you wanted, so consider these your labels. So if you actually wanted, you know, the y hat, what we actually do is we take the individual items based on the labels. So for here, it's going to be the 0 index, which is, I think, let me just run this one just to be sure. So this one is 0 index, so it's going to be this value. So these are just, consider them like your, you know, maybe say your output probabilities. And then this one is 2. So I think 0, 1, 2, so it's going to be this one. So it's going to be this item and this item, and these are the ones that you actually need. You know, just pass those to a log function, and you get your, you know, your what's called the negative likelihood, right? So that's what you get, and you can see it implemented here. So that's what's being done here. So it's the same operation that you see here. That's what's happening here. You pass in those values from y hat, you apply some log to it, and then, right, the negative sign there, which is important. And that's your very simple implementation, right? And that's your cross-entropy loss. I guess also PyTorch offers you this, because we're implemented by scratch. You know, you can see how it's being implemented, but you can actually just use the PyTorch one, which is a more efficient implementation. Okay, let's do that. So you can see here that we pass it to y hat, we pass it to the real values, and that's what we get as the loss. So how to calculate accuracy? Pretty similar stuff. You actually need the same information, the y hat and the y, and you know, to take. So for this one, you actually need to take the, I think the max, I believe, of each one of the arrays, if I'm not mistaken. So you're gonna get the index, and that's what you get here. So now you take that and you actually compare it to the y, which are the real values. And so once you make that comparison, remember the y is just like this one hot encoding, right? So actually when you get the indexes here, that's what you compare it with, and that gives you the result. So now, you know, if it's a match, it will give you a 1. If it's not, it gives you a 0. And so once you reduce the sum, it gives you the number of corrects that you actually got. And that's how you calculate error. There are many ways to implement this, but that's how they have implemented. So the number of correct predictions right here. So you can check it. So in this case, we had 0.5. So at least half of them were correct. Okay, so from here on, it's just going to be a bunch of classes that we implemented. I'm running out of time, but I want to make sure we have some moment to discuss a few things. And if you have any questions, I'll take those, but I'm just going to go through this really quick. You can see it's a lot of code. By the way, there's a lot of stuff missing here. I just try to take the ones that are important and just try to explain it to you a little bit, and just to make sure you understood a bit more. So this accumulator function, really nice idea, I think. This one I haven't thought about before, but I think it makes sense, and I'm glad they actually decided to implement this. So this accumulator is just going to collect some metrics for you, right? Like number of predictions and number of correct predictions, and you know, basically that's determined by this n variable. So whatever information you're collecting, you kind of just you determine it by n. And then it does some, of course, whatever you're passing it is going to collect and it's going to accumulate, right? It's just going to accumulate that result, and that's determined by this right here. It's going to accumulate whatever, if it's a number of prediction of correct prediction. So that's really great, and I really like this idea. So take a look at this function, try to use it, makes sense. Okay, so here is just an example. I kind of wrote this code here just to show you, for simplicity, to say what it's doing. So imagine this one, this is your n, is 2, maybe 2 metrics that I'm interested in. And then I print them out, so it's just this one, right? And then if you know your Python, this is just a list comprehension right here, right? And it's basically what it's doing is iterating over the items in this array, which is test. and then just adding that b, which is uh, maybe, so in this case the items here, right? This could be something else, but the item that I'm passing in the arguments. So it's going to take 5 plus 0, 5, 10 plus 0, 10, and that's what you see here. So that's just the example I provided you for in case you want to learn a little bit more about that. All right, so how about accuracy as well? So, right, when you have a data iterator, you can actually take advantage of that to come up with your accuracy. Again, you can see the data iterator being used again and this is how you want to do it, right? So you want to leverage that because this is the most efficient way to do it, at least in PyTorch. And then you just accumulate some metrics there as you iterate over the data. And that's the really usefulness of this function here, accumulator, that's being used on 2 metrics, number of correct predictions and number of predictions. Okay, so take a look at that. I think that's quite nice. Oops, I missed something. What did I miss? Oh, this one. Wait, I did that one. I did miss something. Okay, so it says W. Just try to do this quickly here. Yep, the most important one of them all. I didn't run. Let's see. Okay, so now I think it should be good. There we go. Oops, I was printing out something here. So why was I printing? Valid matrix. Okay, don't worry about it too much. Okay, so I'm just going to skip that, but you can see everything is shown there. All right, so I think once you have that part, you have your softmax function, you have your cross-entropy loss, and then you're ready to train. You have the data properly formatted using the PyTorch built-in functions, and you're ready to train this model. So now I think this is the easiest part. You learn how to use the zero grad, the backward step, the same thing, right? It's the same thing over again. You determine your optimizer, and you're basically doing the same thing over again. And that's why I say, like, it's going to be more important to use something like PyTorch Lightning to actually, if you're going to reuse things to do more experiments on these models, or you're establishing more variants of the model, maybe you probably can take some advantage of that, because you're going to maybe use code over and over and try to, you're duplicating code. Okay, so okay, animator. This one is just for animating some plot that we're going to see later on, but that's important here. And we're ready to train. So we see the epochs here. We are collecting some metrics, right? So this train epoch is actually doing all the training. So you can see here that we iterate over the training data. We're collecting all the metrics that we need, right? Using the accumulator that we saw before, and we're doing those 3 steps, and we're done. That's basically how you would train the small. Let me see. Okay. So that takes care of this, and then again, just doing some accuracy, and then adding that to this plot, this animation that is going to plot the results. And these are just some, maybe some sanity checks, just to make sure that what the model is outputting are the right things. So this one is becoming more common these days. So whenever you see this sort of assert statements, that's basically a sanity check right there. Okay, so let's see, and then we have the updater. Then this updater is just the SGD function. And once you have your updater, so you can actually implement your own, or you can use the PyTorch one, whoever you want, right? You can actually just pass the PyTorch one. You can actually try that as well with this code. As your updater, just try to use the one from D2L, or you can use the one from PyTorch. We already showed you that at the top. So try it both ways, it should work. I don't know. So I know what's the problem and why I'm seeing that now. It's actually something I did. I changed one of these functions and I was printing out something. Yeah, this is the part. But anyways, don't worry about that. You can actually change that if you just find where that I'm printing that out and just comment it there. I'll do it before I actually post this for you all to access. Okay, so it's doing something. It's training. Let's see what the final result looks like. I would have been really cool to show you, what's the point of the animator class, but I'm printing out something here and it's really messing things up. But don't worry about it too much. Okay, I think it takes 2 to 5 minutes. So in that space of time, I'm gonna take a look at the chat. Yeah, so 2 weeks, most people want 2 weeks. Okay, let's do 2 weeks. Let's stick with 2 weeks. I think 2 weeks is going to be enough. And you know, if you get stuck, please reach out in the Slack group and ask someone for some guidance. I think that's okay for um, this particular assignment. But ideally, what I would want is like for you to actually implement it. That's how you're going to actually learn this stuff if you implement it yourself. And this is the point in time where you want to actually do that. Later on, this stuff is not so important, but understanding the intuition behind that, it will be very important for you going forward. Okay, so let's see. Let's check. And yes, I'm going to provide this code, this notebook. This notebook is what you will need because you're going to just reuse what I provided here. Let me see if you have any questions. There's a lot more conversations than anything, which I really like. And questions. People are actually having conversation and asking really good questions. So one question here, really interesting. So one image augmentation contribute to overfitting? Well, again, there are many ways to actually take care of overfitting. We haven't discussed overfitting yet, but the topic of here, we are just basically building simple models. We haven't even discussed that yet, but yeah, at some point you can run into overfitting, but there are different ways to actually take care of overfitting. But augmentation in general is, augmentation generally is used for in some cases even addressing the overfitting problem. So I don't know. It all depends. Obviously, I cannot guarantee that this is the case. If you will have to, it all depends on your use case. If you have smaller data sets, bigger data sets, or how much data set you're dealing with, what kind of models you're training. So there's a lot of things that we have to discuss before even touching on that topic. Okay. Let's see, anything else? Yeah, and here you go. Augmentation is a regularization technique. So as far as I know, that's actually the case. Okay, so, right. Okay, so so this is the result, right? You see how this one here is the training loss, and we have our training accuracy. So this is a very healthy model. It's doing really good on this data set. And so if you really want to test it, you can actually run this code, which was provided as well. So to perform the prediction, which is great, because if you go into, again, if you're going to, this is so annoying. I'll have to fix that. Let me see where that is. Where am I printing out? Oh, yeah, that's the reason why. Okay. Good thing it's just a very simple demo, but okay, there we go. So, all right, so you see here, we have some examples. Notice the model is doing really well, right? So you can see that there is, the ground truth, and then there is a prediction. You can see it's doing quite well for these images in particular. So you can always just test our predictions. I think that'll be it for the coding walkthrough. Hopefully you learn a bit about this. I hopefully I explain things clearly. If there's something that's not clear that you didn't understand, or maybe you want further references for, please let me know. Please let us know in the chat, and we can help you out. There's definitely a lot of people are here, like from what I see in the chat, very knowledgeable already of some topics, and even things related to PyTorch, which is great to see, because I think we can support each other as we go along. And obviously, I think to make it more interesting, I don't just want to do like going through each chapter and just pulling code from here, because you can actually do that, but you will start to see new stuff, right? I try to incorporate stuff that I've actually built over the years, like my own notebooks for teaching and my own examples. So I think those will be interesting to give you more of an idea on how to use these tools. Okay, that'll be it for your presentation. Any questions, anything that you want to comment on? Thank you so much to all of you that joined and were part of the discussion. That really helps a lot. It really encourages people, when we work as a group, when we do this collective learning. I think it really helps people a lot. I see a lot of sharing going on, which is so amazing to see, and so encouraging for me as well. Because if I were doing this alone and I was just like talking and no one is actually responding, it's kind of weird. But I like to see the participation. So thanks. Any questions? Anything? We still have 10 minutes. I'm running out of voice here, but I can still go. I could do this for hours. I'm really trying to do this for hours. You're welcome, Tina. Really glad to hear that you're learning a lot from the group. And that's why I said the group is doing such an amazing job. I think it's a really great group, really helpful. Everyone is just like helping each other, answering questions. So, you know, as a collective unit, I think we're doing really amazing. And I like the pace as well, and the participation. So thanks a lot to everyone. So what would the linear regression, by the way, there was I don't know, remember, I think it was Simon. I don't remember quite well. So he shared, let me take a look at that. So he shared, I think in our Slack group, he shared a really nice, if you really want to go, yeah, this one. So Simon shared this tutorial here, which he actually put in we included it in the reading material. So I really love this stuff, man. Like when people do this stuff, it really encourages, I think, others, because you can see here, he takes this really approachable way of explaining the key concepts of linear regression. And he even has, like, you know, this really nice slider here that you can use to investigate it further. If you are working on tools like this and, you know, blog posts, which this is what I encourage people to do, please do it and let me know. I'm going to help you, like, spread it out to other people and help share with other people. I'll be okay doing that. And that's why I encourage Simon to submit a PR. This is going to be helpful for a lot of people. I actually wanted to do something like this with blogs, but recently I'm just spending a lot of time on research, so I don't get a lot of time to write. But I'm glad we have people like Simon that do this kind of things. And you can see here. And so when you're, you know, we said actually you could get some ideas here on how to actually get the partial derivatives. I can already see that there's some implementation of at least the equations that you need. So take a look at it. I'm just gonna give you some hints. Yeah, so just for the linear regression part, it doesn't need to work with the softmax regression. Just that part. Just let me show you. Like, just take this one. I mean, if you want to take it further, go ahead and do so. But I think, yeah, just this part right here. So that's where I put the assignment. Just this part. If it functions with this, if it works great with this, so all you basically have to do is just do this, right? Copy and paste it on another block of code here, and then try to have your own function which you're going to use here. Because everything else you have done manually, but I believe that you can actually implement this manually as well, this step. Okay, so just this part. The rest of stuff, you know, doesn't really need to be compatible with the rest of the notebook. Yeah, I almost missed the question, but Josh is asking, what would the linear regression style bare minimum approach be for trying to classify the iris data set? Okay, good question. There's always a little bit of controversy here. Shouldn't be controversy, but so what can you use? So there, even before we touch on linear regression, there are other ways to actually classify, you know, things. There's other methods as well that you can use. So, you know, you can even use clustering, for instance, as well. So there are many different ways you can actually do this. But if you want to, I've never actually implemented the linear regression with the data. I mean, I never touched those basic data sets. I actually just started with PyTorch. No, when I started with PyTorch, what I'm meaning is when I started with PyTorch, I actually just went into the documentation and tried to use their data sets. So this data set is not there. So, but I think you can use linear regression, but I'm not sure what's kind of the basic. I'm pretty sure there are other examples online too. Yeah, Rodolfo actually shared a link. Yeah, and that would be a great way to try. But I think the data sets provided by PyTorch are a great way to start, and, you know, try to implement this as well with some text-based data set. That could be something challenging worth trying as well. Yeah, I mean, most books actually talk about the iris data set. I think if you can get a hand on the hands-on ML book, I think by, I don't remember, I think it's Aurelio, I think he actually uses the iris dataset, if I'm not mistaken. I read the book quite a while back, but I think he uses this one, and he actually implements a linear regression model, I think. But I'll have to check on that again. Maybe that can be helpful for you. All right, any other questions? Yeah, so many approaches. Actually, on that note, maybe what you can do is, I think we can take advantage of it. Since we're learning here, you can go to scikit-learn, right? This is something I actually use as well for learning. Scikit-learn was my first, machine learning based tool that I used. And I always came here to look at the examples. Like there's a lot of examples like PCA on the iris dataset. That's how I understood PCA. And I think there was some k-means as well, clustering applied. Let me see if there's something here. This scikit-learn tool is really good. It's very good at education as well, and it has a lot of examples that you can try to use. Yeah. But that's another route that you can take. Okay. Yeah, I didn't see linear regression, but maybe there is. I'm sure there's many examples that are really, really, really simple. Okay, so good question from Faiz. I think this question will come up again. So is the learning rate in any way related to accuracy or the error rate? So ideally, that's kind of what we want to see, right? So we want to see as let me show you the graph. Ideally, that's what we want to see. It's a very, very important question. So let me show you it here. Okay, let's see with all these numbers. Okay, so here, this is what we want to see. This is a very healthy model, as I said, because you can see the loss is going like this, and the training accuracy is going like this. I mean, the testing accuracy, which is an important one, but you can see that both of them are going like this. They're training this way. So that's really good to see. But as we keep training this model, what's the pattern? Or what kind of pattern do we get? Or what is the trend? So, you can actually test and train this for longer and see what's going on. You will see something really, really interesting, which is at some point, right, you will see that it doesn't even make more sense to keep training this. There's going to be at some point where you get your good acceptable training loss and then training accuracy. But sometimes what you see is you never always get this, right? So sometimes what you see is that the training loss is going like this and the training accuracy is going like this as well. So it's going down. So what's going on there? So there are different cases like this, a mixture of cases. And that's why we see different efforts to deal with underfitting, overfitting. So these are the topics that I think is going to be really important to explain later on as we move along. But at least for today, we want to keep it really simple. But it's a good question. It doesn't always have to be related, right? So you even saw how they're actually computed very different, like using different functions. But again, the relationship between these two is quite important to actually diagnose your model and understanding if your model is actually generalizing well or if it's failing, it's underfitting or overfitting. But we're gonna get to that. We're just getting started. Okay. All right. So any other questions? 2 more minutes and we're good for today. Thanks again, everyone, for joining. Hopefully it's going well and you're getting a lot from the sessions. I'm enjoying doing this, by the way. I'm enjoying it a lot. If you have any questions for me, let me know. I'm in the Slack group. These days I'm really slow to answer, but I'm trying to help out and support the group as much as I can. There's so many projects going on, and I've kind of sliced my time and tried to help people in the group as well. But I'm doing my best, and then I always try to answer you at some point. Okay. So thanks and have a good day. Bye. Enjoy the weekend.